We are looking at the digital CDR. The idea here is you generate a number of phases of a clock which spans one cycle, okay, and you can pick one of them. Conceptually, this sounds fine, right? Because obviously, like one of those phases has to be right. That will be in the middle of the data symbol interval. Now, how do you pick that? We use exactly the same algorithm we used for analog CDR. Okay, there we were delaying and so on. Here you just have to pick one of them. Okay, so now I will show this block as a sort of digitally controlled delay. Okay, where it's controlled by this N control. Okay. Now, the way this is usually implemented is you have somehow you have a multi-phase clock generator. Okay. It may give like 4 or 8 phases. Okay. So, which means that it will be, the waveforms will be like this. Let me show them. Let me show triangular waveforms. I mean, it doesn't have to be like this, but so this will be 0, then you will have 90, oh sorry, this is 180, and then 90, and then 270. Okay, so let's say we did have triangular waveforms like this. Then you can generate a lot of intermediate waveforms by weighted addition. Okay, so if you take, let's say, alpha times ck0 plus 1 minus alpha times ck90, what happens is you can get edges between 0 and 90 degrees depending on what alpha is. If alpha is 0, you get ck90. If alpha is 1, you will get ck0. And as you change alpha from 0 to 1, you will get all the edges in the middle. Now, if these are exactly triangular waves, then as you step alpha, there will be a linear change in the time shift. Okay. So, this business of generating this stuff, this is known as phase interpolation. And I'll assume that this alpha is the input to that. Okay. And finally, you get maybe 1 or 2 phases. Typically, you need both positive and negative, basically a differential clock, okay, of the right phase. So you will get it from this phase interpolator. But as far as the modeling is concerned, I mean, the whole thing can be thought of as some input clock which is delayed by this. Is it okay? So now, the way this control has to work is, I mean, you generate all the phases from okay, meaning you don't have to keep all of them available all the time, right? The phase interpolator, depending on the value of alpha, will generate these phases. Okay, and the digital control also should be such that it goes from, let's say, 0 to some maximum. Okay, and then so that means that maybe you go all the way from, let's say, clock 0 to something just before the next one, where the edge is over there, okay? And then it should wrap back to clock 0, right? This is how this is how phase works, right? You just have to wrap it back to the original one. Is it okay? So that's you assume that the control voltage goes from 0 to n max, and then each of these numbers gives you some phase, which is, I mean, as you increment this digital control word, the phase will be uniformly stepped. Okay, and it will be stepped by some minimum interval. That will be the LSB, the least significant change in the phase interpolator, right? So that has to be sufficiently small. Now, initially I assume that it is kind of really small, and then later you can figure out how much you need. Okay, this is fine. So this is what we did and saw that if you have data and I will show it again as a digitally controlled delay. It could be that you can make that also. You can make a digitally controlled delay. You take the same analog delay line and then drive it with an A to D converter, then you will get a digitally controlled delay. But usually that's not how it's implemented. It's implemented using a phase interpolator. Okay. And we saw that if we take up minus down and pass it through an accumulator, Z inverse by 1 minus Z inverse. Okay. So essentially, for each up pulse, the output gets incremented by 1, and for each down pulse, the output gets decremented by 1. Now, in the earlier case with the analog clock and data recovery circuit, for each up pulse, the voltage on the capacitor would build up by some amount, right? It is ICP times the symbol interval divided by C, okay? And that will cause some delay in this. So that is the unit change in delay. Now, if you make the LSB of this same as that unit change in the delay, these two will behave in the same way, okay? That's what we calculated. This pi LSB should be 2 pi times ICP times KD by C for these two to be equivalent. Okay. And you do this one, and then this Z inverse by 1 minus Z inverse, the way it's implemented is that this is a digital adder, right? This thing is a digital adder, and then you have Z inverse here. Okay. So the transfer function from this input to that output is Z inverse by 1 minus Z inverse. Okay. Now, how do you make this Z inverse for digital signals? It's a flip flop. Basically, it's a set of registers. It's called a register. Okay. And when you talk about digital signals, it will have some width. Okay, some number of bits. So obviously, this output here, this N control, the output number of bits of the output of the accumulator should match the number of bits that are required to control your phase interpolator or the digitally controlled delay. Okay. Usually, it will be 6 to 7 bits of resolution. I mean, that is good enough to place the clock accurately, right? 7 bits means that the LSB is slightly less than 1% of the clock period. Okay, so that kind of error is good enough. Okay, because if you try to make the LSB smaller, you have to have a much finer phase interpolator that increases the hardware and power dissipation and so on. Okay. And you may not be able to implement that accurately either. Okay. So this is how it is. Conceptually, this is what it is. And essentially, when you have a single accumulator and something like this is up and down, the whole thing is equivalent to an up-down counter. right? You have up here and down there, and that's all. Okay, this is fine. Any questions about this? So this is actually a favored way of doing things these days. I'll go to the clock and data recovery circuit without forwarded clock, and it becomes clearer why that's so. Now, what happens when you don't have forwarded clock? Can this thing work? You have to recover both the phase and frequency. Can this work? Or what do you have to do? Accumulator? Okay, how will that help? What is the difference between the cases with forwarded clock and without? What is the difference? There can be a frequency error, right? That is, so obviously there is no clock coming in from the other side. You have to generate it locally. Okay. So you take your somewhere you have some clock, and this clock could be at a different frequency than the data that is being transmitted. Okay, and then this goes through a digitally controlled delay. Okay, or a phase accumulator. You can think of it in any way you want. Okay. So now the question is, can you generate a frequency here that is different from this frequency? You will have to do that, right? Because you have to somehow correct for the frequency. Okay. Earlier we were actually playing around with the control voltage of the VCO, which changes the frequency. Right now we are not doing that, right? We are only using a digitally controlled delay. Okay. And this frequency is fixed, and this frequency could be different from the transmit data frequency. Okay. Of course, if I have to clock the data that is being transmitted, then the clock eventually has to have the same frequency. Otherwise, I'll not be, getting one sample per bit, which I need for correct decoding of data. So the question is, using a delay line, using a digitally controlled delay, can I get a different frequency signal? Is that possible? What's that? You have to increase the delay. How do you do that? I mean, what should I do actually? So I have this box, right? Uh, I have this, okay, and let's say that this goes from 0 to n max, okay. The delay goes from 0 to something, okay, or something to 0, whatever it is. So how do I, from this, with this, I have to generate a clock of a different frequency. Can I do that? So the input clock, let's say, is like this. Can I get an output clock of a different frequency? And of course, you assume that the LSB is something small, some fraction of a period. Okay. What's that? So basically, I have to change it in every clock cycle. Okay. I mean, later actually we can change it over some number of clock cycles. But what I'm saying is, so let's say the delay value is 0 here, and by the time the next edge comes, it's a little more, and by the time the next one comes, it's a little more, and so on. Okay. So the delay, what is This is why that phase picture helps, right? If the receive frequency is different from the transmit frequency, okay, this is the difference. So now FTX minus FRX will be something like that. Okay. So essentially you have a delay line or basically a phase delay, and that phase delay has to be a ramp. So that means that this control voltage has to keep on incrementing in every cycle. That's all, right? So you can see basically you can make the cycles longer by having some delay for this rising edge, larger delay for the next rising edge, larger delay for the further next rising edge, and so on. So you have to keep going like that. Is this okay? So like this, you can generate a different frequency. It's very obvious from the phase picture. The phase difference between two signals of different frequencies is the ramp. So if you give a ramp control voltage to this, it'll the output will be a signal of a different frequency. Is this okay? So that's what we'll do. And anyway, actually, we could have done it directly from the phase domain model of the analog CDR without the forwarded clock also. Okay. As long as this thing goes from 0 to 2 pi and wraps around, you can keep on doing this, right? So you will get a different frequency signal. Okay. So now, if you look at the analog CDR without forwarded clock. By the way, we can get the digital CDR without forwarded clock by reasoning it out from scratch, but we've already done the work to derive the analog CDR. We can kind of follow the same thing. Okay. This is a bang bang phase detector. Okay. And sorry, what we had was something like this. Okay. Right. So again, we can get the digital CDR by making the, so in case of the digital CDR, what we have is, we don't have this VCO anymore, right? We don't have a variable frequency generator. Or rather, we don't have a variable frequency oscillator. So what we have is the following. So we have some local clock CK0, and again you can think of this as a digitally controlled delay line. Okay, and I have to feed in N control to that. And gives me the clock. Okay. So now the question is, what should be here so that the behavior of this clock is the same as what we had in the analog CDR. Okay. So how How do you make the equivalent? Oh, sorry. Uh, I made a mistake here. Obviously, none of this is here in the digital CDR. I have up and down signals going into some signal processing block so that the signal processing block should generate N control in such a way that the phase of this clock, let's say that I already have an analog CDR design and its performance is satisfactory, I just have to convert it to a digital CDR. Okay. So then all I have to do is like use this digitally controlled delay line, and then I need to make sure that the in response to output of the phase detector, the phase of the clock behaves in the same way. Okay. So what should happen? How do you go about finding the equivalent? We did this for the case with the forwarded clock, right? So what should we do? To make it exactly equivalent, that may or may not be realizable. I mean, there may be other constraints that come in, but what? Huh? Up down counter. Okay, is that enough? That's the question. Huh? Okay, so what should this have? I mean, you can take a hint from this, right? You have up and down here, and the control voltage is over there, and the phase is here, right? So, and we've already evaluated the incremental model of this and so on. So, the phase of this clock, what happens to it as a response to, in response to, let's say, a single up pulse? Yeah. What are the, I mean, there are two components, right? What are they actually? Yeah. So, what does each of those things do? So, because of a single up pulse, okay, what happens to VR? Okay, so pulse, right? Pulse of amplitude, ICPR, and width of one cycle. Okay, but what is the consequence for the phase of the clock? Really? I mean, fine. What happens at the end of the cycle because of a single up pulse? Please work it out. In response to a single up pulse, what happens to phi ck due to the integral and the proportional parts? So what I'm looking for is up. We get a single pulse. That means that this is for a duration t naught. Okay, and we have down and so on. That doesn't matter. So then I have RC and a VCO with some gain KVCO. Okay. So what I want is the incremental phase at the output in response to this. That's all. Okay. And do it. There will be two components, obviously, because the whole system is linear now, right? So there will be part due to VR and VC. You can plot the two separately. You can plot it for a few cycles. It will be very obvious what it is. Our pulse looks like this, right? This is T naught, then we have 2 T naught, 3 T naught, and so on. Okay. What will be the resistor voltage VR? What is it? Yeah, it will be a pulse. Okay, of amplitude. The shape looks the same, right? Okay. Now, what is the phase change due to this? How would you calculate this? Basically, you have to compute 2 pi KVCO integral VR dt. Okay, what will that be? It will ramp up like that and stay there, right? And what will be the height? 2 pi KVCO ICPR T naught. Okay. So now if I look at the values at the end of every cycle and call that my change, phase change in discrete time, what is that? What is that function? No, I mean, give me like function of z. What is this thing? If I have it like this. Sajay, what is this? No, step is fine, but what step is this? Yeah. Just tell me as a function of z. If I had to write this whole signal as a function of z, what is that? Yes? Yeah, z inverse by 1 minus z inverse times what? What is the amplitude here? This whole thing, right? 2 pi KVCO ICPR times T naught. Okay, this is exactly what we got, right, for the case without the forwarded clock. And this is what we implemented. We just said that if this is the LSB, right, then the filter has to be just this and the scaling factor is introduced by the LSB. That's all. Okay. Is this fine? We just made that the LSB. That may or may not be the case. So now what happens to VC in this case? The VC will do that. Okay, what will be the height of this? ICP? Huh? No, this is VC. What is VC? ICP times T naught by C. Okay. So, in response to a single up pulse, this is up and the control voltage does that, where this height is ICP times T naught by C. And what happens to the phase of the clock? Huh? So this part of it, the phase does that. What is the increment because of this? What is the increment? How much is it? ICP? Yeah. No, what is, you have 2 pi KVCO, all the stuff, right? 2 pi KVCO, ICP, T naught square by 2C. Okay, so that is the change in the first cycle. After that, what happens? What will be the shape? Huh? Ramp. It will be a ramp. Now, what will be the slope of the ramp? the slope will be, what is it? What is the slope of the phase? It is the radian frequency, right? Radian frequency step. And how much is that? It is this voltage times 2 pi kVco. Okay. Slope is 2 pi kVco ICP T naught by C. Okay. And how much does it change in every cycle? This times T naught. That's all. Right. So this step per cycle will be 2 pi kVco times ICP T naught square by C. Okay. Is this fine? So now if you had to represent this as a discrete time signal, what would that be? I have something like this, right? I have some initial part which has some shape, and then after that it's a straight line with some ramp. Okay. This is phi 1, and the increment per step here is like phi 2. So how would you represent this one? What can you represent this as? Yes. I mean, just decompose it to some known signals, right? What signals do you know, first of all? Discrete time, the standard signals, impulse, step, what else? What do you need for this kind of behavior, right? Ramp. Certainly you need a ramp. So what ramp would that be? Is this exactly a ramp? It is ramp plus something. What is it? Huh? Ramp plus step, right? So this is the same as you have a step of phi 1, okay? And this can be represented as phi 1 times Z inverse by 1 minus Z inverse. And then the rest of it would be like that. What is the representation for that? What function is this now? Yeah, I know, but what is it? Tell me the expression in terms of Z. Is it Z to the minus what? Oh, sorry, this is here minus 1. I don't know why I wrote 2. This is what that is, right? Is this correct? And what should be the coefficient? No, in terms of phi 2, what is this? Phi 2. No, no, this is a discrete time, this thing, right? This is phi 2. Okay. So now, essentially, if I look at the phase at the end of every clock cycle in this system, and in response to a single up pulse, I am getting what is a single up pulse correspond to an impulse at the input, right? And the response to that is I have due to VR, I have 2 pi kVco ICPR times T naught times Z inverse by 1 minus Z inverse, and due to VC, I have two components. What is it? 2 pi kVco ICP T naught square by 2C times Z inverse by 1 minus Z inverse, and the other part is 2 pi kVco ICP T naught square by C Z inverse by 1 minus Z inverse square. Okay, is this fine? So what should I implement in the digital domain? I mean, this should have been obvious just from our earlier phase model. So what should this have inside it? What should it have? We calculated some things now, right? Let's calculate, I mean, let's associate it with the LSB size and all those things later, but functionally, what should it have? Huh? Yeah, I know, but what is the signal processing block here? What should it have? Two? Two accumulators. I mean, this is what we had earlier also, right? You need one accumulator to correct for the phase and the second one to correct for frequency. If you had it with only one, if there is a frequency error, there will be a constant phase offset. So then, to compensate for that, you have to measure that phase and then slowly keep on changing the frequency. In this case, that is like an additional ramp to this. So you have to take the difference between these two. Please think about this because somehow many of you, I think, were not able to calculate what's going on, or I need to have these two, and I need some weighted addition. Okay, I'll just show it as some C2 and C1, some weighted addition to do that. Okay, please think about this. Probably it wasn't very clear, but we can revisit that in the next class. So hopefully this is the part we had, only the first part, right? First integrator we had for the case with the forwarded clock. For the second one, now if you have a constant phase difference, right, you will keep getting some constant signal here, right? And based on that, you give a ramp so that the frequency gets corrected. That's the idea. Okay. So now you can also make this exactly same as the analog CDR. I could have derived this from scratch, but since we had already done that, I thought we'll use the phase model of that to derive it. Okay. Hopefully the part without the forwarded clock was very clear, and based on that you can calculate it. And from this, I think now you have already done the assignment, right? So you can calculate the magnitudes of these different things to see what the LSB should be, etc. Okay. Finally, I mean, if the LSB comes out to be too small, you don't try to implement that, but you just live with a larger LSB and then do some quantization. It introduces some more errors. That's all. Okay. Please think about this. The digital CDR without the forwarded clock, and it needs, just like in the other case, we needed a proportional and integral path. We need an integrator to follow the phase and then another integrator to follow the frequency error.